Okay, good morning, everybody. Hope you are warm this weekend. If you want to take a picture of this on the next slide, this gives your whole overview of this unit so you know all the dates. Today we're going to finish up the principles of evolution and we'll get into the next lecture. We are going to set up labs 22 and 24, so I'll walk you through all of that. And then the rest of the lab, those are pretty quick to set up. We're going to finish lab 21 except for page 8 and the discussion questions 7 and 8. So for homework, I want you to finish up lab 21 again with exception of page 8 and discussion questions 7 and 8. Your other homework is to continue working on your study guide objectives for evolution. Write them out, go over them, begin quizzing yourself. Review, quiz, review, quiz. Here's the rest of our unit. So the rest of our unit just gives you the dates of what we're doing and when. I modified things a little bit from the syllabus for this unit because we missed that first day. So yeah, if you want to take a picture of this so you just have it on your phones. I think I also messaged it out to you yesterday, I believe. I'd like us all to be on the same page. So let's pick up where we left off. What page? Let me see. We were about to talk about comparative anatomy. So let's try and figure out what page we're on. Let's see. We're going to go. Mind. All right, we're on page 81, the top of page 81. That is where we left off. We started talking about the pieces of evolution, the data to support that evolution is a theory that shows that living things change or evolve over time. So we talked about fossils and we talked about skull structure. We're going to continue on. We're going to talk about limb structure. I know we started talking about this. What you saw in lab when you started looking at the four limbs of different vertebrates, and we're talking about vertebrates, we mean any animals that have a spinal column or a backbone. When we're looking at the vertebrates and started looking at the four limb structure, what we saw, or what you witnessed, was that we all as vertebrates have a humerus, a radius on our thumb side, ulna on the pinky side, carpals, the wrist area, metacarpals, the long bones in your hand, and then phalanges. What we saw also is that organisms' four-limb structures are adapted to the way they live their life or the environments that they live in. So the bird or the chicken, they're as opposed to us like this, their humerus is tucked usually pretty close to their body, except for when they're flying. Chickens do fly a little bit. Their radius and ulna then are kind of going upward in their natural stance. Their carpals are bent, bending of the wing. And then the phalanges and the metacarpals, tarsals are in the foot, and the metacarpals and the phalanges is kind of ambiguous almost what bones were what in their end of their wing. So in lab, what I'm just looking for is that you're labeling the tips, the phalanges, and the bones that are closest to the bend or the carpals as the metacarpals. So I always like to think like, what does the animal do? How does it act? It acts like this, right? Chickens go like this. They have very thin, long, light bones. That helps them when they do need to get away from predators and then fly. The frog was interesting because with the frog, they're kind of like this. So their arms are tucked back. The radius and ulna, if you noticed, were fused together. Because frogs jump a lot and jumping is very hard on our joints, they need to have very good, strong bones in their forelimb so that when they are doing that constant impact of the jumping, that these two bones are not thin and break, but they have over time fused together to become one bone structure. And you may have noticed that when you were looking at the frog, that there was just kind of like a little indentation between that one bone here, the radius and the ulna, but they were not completely separate bones. So we do see that evolution of strength in the thicker bones fusing together to allow them to not break their forelimbs when they're jumping a lot. When we are taking a look at the forelimbs of vertebrates, we call them homologous structure. We see this term HOMO a lot in biology. It means similar or same. Just like people who are homosexual are of the same sex. We also see hetero a lot in biology. Hetero means different. People who are heterosexual are different sexes. We will talk a little bit more, maybe today or maybe next lecture, about homologous chromosomes. There's that HOMO again. That means similar. When organisms have similar structures like forelimbs, it gives you the indication that they have evolved from a common ancestor. We started talking about this the other day. I just want to reiterate this. That all vertebrates have a common vertebrate ancestor. And as the vertebrates got in an area and things began to get crowded, the environment got crowded, there was competition, and we'll talk a lot about this as well, that competition favors organisms. I mean, competition does not favor organisms. If you have to constantly compete, you are risking your survival to stay alive. Just like if I told you all, oh, by the way, I only give out 2 A's in this class. Everybody else gets an F. Would that make our class structure a lot more anxiety-ridden, right? You might start to deceive each other. You might start to sleep less because you're like, oh, I have to get that A. I'm going to study, study, study. That competition would definitely harm you. Like when we're talking about a group of organisms, when they live in a certain area together and things start to get crowded, one of the things that we do know is that when reproduction happens, that mutations happen by chance. And some of those mutations give you favoritism or an advantage in the environment. Let's say that you are part of this group, the original vertebrate group, and you have a mutation that causes your bones to be like have holes in them and be lighter, and you find that you can flap your forelimbs and you can fly a little bit. So that what you can do is you can go up into the sky. And you could maybe even get to the tops of trees where you can get food that the other vertebrates can't get to because you have this mutation that just happened by chance in the copying of your DNA from your parents to you. So now, because you have this adaptation, you might go live in the trees, or you might go live further away from this crowding where there's a lot of competition for resources, food, mates, etc. And you're like, I'm getting out of here because this totally sucks. So I have this other adaptation that happened by chance, and I'm going to go live somewhere else where it's not crowded. And I can just feast on everything I want. I don't have to fight for a home. I don't have to fight for space. I don't have to fight for mates. I can live over there and relax, whereas everybody else is scrambling for survival. Other mutations happen by chance that allow some of these in the group to go and live in maybe like grassy lands and some have nice fins that they have a mutation. Instead of having their phalanges singular, they get a fin-like structure which allows them to swim better. So they go to water. Some of them who can fly can go further places. Some of them maybe live on trees or in trees. And so what you see happening with the mutations that are just happening by chance is that from this group that is fighting for survival, that as mutations just occur by chance, they start going into different environments that suit their mutations better, and it lessens competition. So again, what we do know is that they came from that common ancestor, and mutations allow us with variation to go into places where we have less competition for resources. So again, vertebrates are bones. We call them the forelimb, not four, but fore meaning front. So you have to think about all the different vertebrates. What's their front limb situation? Do they have arms like us? Do they have fins? Do they have wings? Do they have hoofs? The phalanges of goats, for example, because goats have hoofs, is that the phalanges and the metacarpals are fused into a hoof structure instead of having a big separation because they are pounding on those. And again, I mentioned all of these bones and you went over them in lab. For the most part, the bones are the same material, but when you take a look at bats or birds or organisms who fly, they developed mutations that there are holes in their bones, which make their bones lighter. You could see with the bat how skinny those bones have become that allows them to lift their body weight and fly. What we call this is we call this divergent evolution. When something diverges, it goes away from the middle. So in my illustration here, because the arrows are moving away from the common ancestor, organisms who have homologous structures show divergent evolution. They're moving away from the common ancestor. If something moves toward a common ancestor, it's called convergent evolution. So this, when we're talking about homologous structures, organisms are moving away from the characteristics of the original common ancestor. They are diverging away. They're going in an opposite direction. You saw many of these in lab. So again, just to reiterate that you have the same, or I should say similar, bone structures. The humerus, the radius and the ulna, and I'll talk about this in just a second, the carpals, the metacarpals, and the phalanges. And we see that with the colorations of the different bones throughout the vertebrates that are displayed here. Interesting things that have happened over time.